welcome you all to this 6th webinar of the Graduate Program in Physics of the Federal University of Pará in Amazônia, Brazil. I ask everyone to kindly leave your audio and video sources turned off, except for the moment you're going to speak. Questions will be allowed after the webinar, unless otherwise requested by the speaker. The questions can be made using the chat. Well, today we are honored for the opportunity to hear from Professor James Burkett Hartle, who is a member of the U.S. National Academy of Sciences and a fellow of the American Academy of Arts and Sciences. Professor Hartle has never visited our graduate program in Amazonia, and therefore this occasion is even more special. Professor Hartle received his PhD from Caltech under the direction of Murray Gell-Mann. Professor Hartle is a professor of physics emeritus at the University of California, Santa Barbara, where he has also been a founder and past director of the Institute for Theoretical Physics. Professor Hartle is the author of a very nice textbook entitled Gravity, An Introduction to Einstein General Relativity, published by Addison Wesley, which I recommend to you all. Professor Hartle is known for several important contributions to theoretical physics, including the Brill-Hartle geom, the Hartle-Thorne metric, the Hartle-Hawking state. And he's a world-leading expert in quantum cosmology, what is the subject of his webinar today. Well, we are here today to listen to Professor Hartle, so that I won't take your time further with this introduction. Professor Hartle, thank you once more for having accepted our invitation. The audience is yours.
Thank you for the introduction. Right. What I plan on talking to you about today, it starts out with a little bit of history. In the period when quantum mechanics was just being developed in the late 20s and early 30s of the last century, it had, of course, a huge impact on physics. But at roughly the same time, there was another development in physics that was also had a huge impact, and that was the discovery by these people, right, of that the universe was expanding. This is a picture of the Abbe Lemaitre. This is Hubble, and this is Vesto Melvin Slipher, who maybe is less famous, but he's the person that measured all the redshifts, which led to this Hubble diagram of distance versus velocity from redshift, which showed that the universe was expanding, because the further away you got, the faster the galaxies receded. The success of quantum mechanics universally, right, means that I think we have to take into account the possibility that the universe itself is a quantum mechanical system. It's an overwhelming inference from the physics of the 80 years that is that separates us from the beginning of quantum mechanics. If that's the case, and the universe is a quantum mechanical system, then it has a quantum state. And the question for fundamental theory is, what is that state? It's not something we're going to measure, because it's the whole universe and we're inside that, but it's something that has to be posed as part of the fundamental theory, like string theory. So contemporary final theories have two parts. They have a theory of the dynamics and a theory of the quantum state. A natural question is, what are the regularities of the universe that are affected by the dynamics, and what are those that are attributable to the taste? And also, I think you have to ask, is there, physics seeks to unify, or for example, the different scales of energies, the strong electromagnetic and the weak interaction, But there's also an unfinished task of unification in unifying the theory of dynamics with the theories of state. They are connected, as I'll show you. You can't just ignore the state in making predictions, because if you're ignorant of the state, you should calculate with a density matrix, which is the unit matrix normalized. But that means there would be no evolution in the universe because it would commute with the Hamiltonian. Its density matrix like this corresponds to infinite temperature equilibrium, which we don't see. There wouldn't be any second law of thermodynamics. The universe would already be at the highest entropy. And no classical behavior, which we certainly see because the fluctuations away from classical behavior would be infinity. It's all inconsistent with observations. So we have to assume that we have a state. Also, if we have a quantum state, if we don't have a state, then we don't have any predictions at all. In ordinary quantum mechanics, the probability P at a time t of some alternative, which is represented by a projection operator, is just a projection operator applied to the state squared, right? The projection operator operates in time by the Hamiltonian, right, if you want it at a later time. So if we don't have both the operator P and the H and the state psi, there are no probabilities and no predictions in principle. Different regimes are affected by the dynamics in the state to different levels. As far as the Hamiltonian goes, the Hamiltonian basically tells us what the regularities of the universe or any other system is in time, right? That's why it was discovered first, because as it turns out, very luckily, physics is essentially local. And so by doing experiments and accelerators and other things, you can figure out what the Hamiltonian is. And it's responsible, of course, for classical dynamics and various laboratory experiments on small scales, not small meaning less than cosmological scales. But the state is responsible for many other features of the universe. It is responsible, first of all, for classical space-time. Classical behavior, as I'll show in quantum mechanics, is not something that's generic. It's a result of quantum mechanical probabilities. It's responsible for the initial homogeneity and isotropy of the universe, plus its inflation. The fluctuations in the ground state, the arrows of time, the cosmic microwave background radiation, the large-scale structure, the existence of isolated systems, the topology of space-time, and maybe some of these other more exotic things. Those have not been calculated, but the number of large and small dimensions and the constants of effective field theories. So it seems unlikely that we're going to be able to discuss anything in a laboratory. Indeed, in all of particle physics, it seems unlikely that we're going to have to, it seems likely that we're going to have to rely on cosmology to reach the highest energy scales. In today's fundamental theories, like string theory, for example, are characterized by the Planck energy, which is 10 to the 19th GeV. So it's unlikely we're going to be able to build a laboratory that will reach those energies. But in the beginning of the universe and in its expansion, we have, you might say, an experiment that's already done, where Planck energies are reached in the very beginning. And there's 14 gigayears of data scattered over many, many light years. So we only have one experiment, and our job is to collect the data, right, from what we see about cosmology and see if it confirms the theory. And that's the subject of quantum cosmology. But my question is, so I think I made a small case that quantum mechanics has affected cosmology significantly. You only have to think of Big Bang nucleosynthesis, for example, recombination that led to the microwave background, and the growth of fluctuations, quantum fluctuations in the early history of a homogeneous isotropic universe that eventually collapsed, right, under the gravitational attraction and gave rise to the large-scale structure of galaxies that we see today, and also the structure of the microwave background. So quantum mechanics affects cosmology. That's the realm here. But most of my talk today is devoted to the other way around, how cosmology affects quantum mechanics. And that is the main subject of my talk today. We, of course, have the Copenhagen quantum mechanics, the ordinary textbook quantum mechanics, is probably the most successful theoretical framework in the entire history of physics. So it's, again, inescapable that it's going to affect cosmology. Copenhagen quantum mechanics that you read about in your textbooks is still being worked on at a fundamental level. It's called the interpretation of quantum mechanics. This slide just shows a bunch of problems that people work on: the non-locality, the measurement problem, contextuality, et cetera, et cetera. I'm not going to talk about any of these. And indeed, these are still not completely solved to everybody's satisfaction. But despite that, despite having these problems, no, as far as I can tell, no mistakes seem to have been made over the 90-year history of the subject. And it's fully confirmed by experiment. It did have problems with it, right, as it says. For example, among them, the formulation of Copenhagen quantum mechanics involved complex systems. It was a theory of measurements that were being carried out, which are often complicated to describe, by observers, right? Observers, conscious observers, who were what the probabilities were predicted for what they would see. But those are very difficult things to describe. It's complex. So it's not as simple as one might hope. But that textbook quantum mechanics must be generalized to apply to quantum cosmology for a number of reasons. First of all, it assumed the division into observer and observed. The object of the theory was to calculate probabilities for observations. But in the theory of the whole thing, there can't be any fundamental division into observer and observed. Especially because we aim at measurements can't be the primary outcome of primary focus of quantum mechanics. Measurements and observers can't be fundamental in a theory that hopes to explain the early universe, where neither one of them existed. No observers, no measurements, and so forth. Copenhagen quantum mechanics also assumed the classical world was external to the framework of wave function and Schrödinger equation. But there's no basis for that assumption. Right? Fundamentally, there are no variables that behave classically in all circumstances. There are a lot of particular variables which behave classically in particular circumstances. But even worse was the problem of retrodiction in Copenhagen quantum mechanics. Following von Neumann, there were two laws of evolution. The first is the unitary evolution of the state by the Schrödinger equation when the system is isolated. Schrödinger equation can be run forward and backward in time. It can be time reversed. But the second law of evolution was the projection or collapse when the system is measured. And that just means that you have the state, measure it, P is the operator representing the outcome, and you reduce the state by projecting it. That obviously can't be time diverse. But what that means is you can't retrodict the past from the present, because the operation of the reduction of the wave packet only goes one way. But cosmology, which we're interested in, is all about the past, right? We want to reconstruct the past history of the universe to simplify our predictions of its future. So textbook quantum mechanics has to be generalized for cosmology. And that's the subject of my talk today. We do have a necessary generalization. It's, as I'll show you, it's in Decoherent Histories Quantum Mechanics. A brief history of the subject, I'll just give you that development. Just the two endpoints. It started with Everett's insight, about 56, that as observers, we're not physical systems outside looking at the universe, we're physical systems inside it, subject to the laws of quantum mechanics, but playing no special role in its formulation. That certainly was the beginning of the subject. The end is what I'm going to talk about today, which is decoherent or consistent histories quantum mechanics, right? That was pioneered by Robert Griffiths, Murray Gell-Mann. There's an unfortunate thing about this slide here that it is on top of Roland Omnes, who also played a significant role in the beginning. It's not a new subject. We're like 40 years past this, right? And it seems to be successful. So I'm going to describe a little bit of it for you today. It has to do with let's consider as a simple example of a simple model universe, which is just a box with everything inside. Observers, experiments, the sun, the stars, etc. The Earth, right? We're down here someplace, right? It's a model universe. Maybe the box is 20,000 megaparsecs on the side. The important thing is there's nothing outside looking at it. The theoretical inputs to predictions are the same as I had before. A theory of the dynamics, that the Hamiltonian or the action, depending on what you want to do, and the quantum state of the system. The output of the theory, H and psi, are probabilities for coarse-grained alternative histories of the universe. For example, you'll get probabilities for the prediction of the Earth's motion around the sun, right? There's no certainty that it moves in an elliptical Keplerian orbit, but in a quantum mechanical sense, in the state it's in, the probability is just very high that it will move in Keplerian orbit. So these are histories of the universe which we can see and test locally. Now, I mentioned that the Earth is moving on a classical orbit. Classical behavior is not something that's given in quantum mechanics. It's a matter of quantum probabilities. A history behaves classically when, in some suitably coarse-grained set of histories, the probability is high for the history of correlations in time, summarized by deterministic classical laws. So decoherent histories predicts probabilities for which of a set of alternative histories happen. In the case of the Earth around the sun, the alternative histories might not have gone on an ellipse, but on some wiggly thing around the sun, it's not certain. The probability is only high for the ellipse, and we have to calculate that. Probabilities for the past can be calculated using sets of alternative histories now, so we can now retrodict the past using decoherent histories in a way that we could not do with Copenhagen quantum mechanics. So decoherent histories enables quantum cosmology because paths are probabilistic. The past is not over and done with. It's a probabilistic statement of what happened in the past. Amazingly enough, the person to say that was Albert Einstein, As he said, the principles of quantum mechanics, let's see if I can get rid of this. Whoa, the principles of quantum mechanics, oops, screwed this up here. Principles of quantum mechanics involve uncertainty in the description of fast events and only uncertainty here. Let's,
yeah.
I'm hoping that this will set up slideshow. There we go.
Great.
Sorry for that. But there's an obstacle to assigning probabilities to histories in quantum mechanics, which is quantum interference. Nowhere is that more clearly illustrated than in the famous two-slit example. Here we have a screen with two slits, the upper slit and the lower slit, and we have an electron gun that fires an electron. It has two possible histories. It might go through the upper slit and arrive at some point y, or through the lower slit and arrive at some point y. And then we have the characteristic interference pattern where the probabilities to arrive on y have this wiggly structure. But if we can't, in this framework, assign a probability to whether it went through the upper slit and the lower slit. The reason for that is that in quantum mechanics, probabilities are squares of amplitudes, right? For example, this is the amplitude to go through the upper slit and arrive at y. And the probability just to arrive at y should be the sum of the amplitudes squared. But the sum of the amplitude squared is not, the sum of the amplitudes squared is not equal to the squared amplitude sum, right? So it's inconsistent to assign probabilities to this particular experiment and expect to, you can calculate the probability that it got at y, but you can't calculate the probability that it went through the upper slit and the lower slit because of interference. So some rule is needed to specify which histories can be assigned probabilities and which can't. Textbook quantum mechanics assign probabilities only to sets of histories that have been measured. Decoherent histories or consistent histories assigns probability to sets of histories that decohere. That is, for which there's negligible interference. In fact, I get rid of those inconsistencies between members of a set as a consequence of the Hamiltonian. So decoherence allows consistent probabilities. Decoherence is a more general, more observer-independent rule than measurement and easier to deal with, in fact. So, for example, people sometimes ask, in Copenhagen quantum mechanics, was the moon there if we weren't looking at it? In decoherent histories, so they can assign the probability of the position of the moon when no one is looking at it. Or what about density fluctuations in the early universe when there were certainly no observers around to observe them or measure them? You can assign probabilities to those to calculate those probabilities, right, just from decoherent histories, quantum mechanics. Complex systems like this, right, can be analyzed, but they don't play any central role in the formulation of quantum mechanics. They're something that might be an output if we were sufficiently powerful, but it's not something to obstruct the how to deal with quantum mechanics. In order to discuss this, I'm going to make a small model of decoherence for you. So let's imagine, here's the two-slit experiment again. Here's the upper slit and the lower slit. Let's imagine that in the neighborhood of the slit, there was a gas of particles, call them photons, let us say, that interact with the electron weakly, so they don't disturb its trajectory, but they can carry away phases. So for two histories with corresponding branch state vectors, one branch state vector is going through the upper slit and arriving at y, up like that, and the other is going through the lower slit and arriving at y. So we need to find out whether these interfere. We need to calculate the measure of interference. The condition for this is that this overlap between Y and S, between the two histories, vanish, right, or is negligible. This toy model we can actually work out right on the slide, the toy model for decoherence. Let's suppose the initial state, it's going to arrive at Y, is a sum of, it went through the upper slit and the lower slit, plus the whole lot of weakly interacting particles, whose states I've denoted by phi. That's these little particles bouncing off here. This evolves into a sum of branch wave vectors. So the amplitude for going through the upper slit and arriving at Y is the state that it went through the upper slit multiplied by the state before the interactions of all these other particles multiplied by S matrices that tell us how they scatter off this state. The same for the lower. So interference vanishes when the overlap between these two is small. I'm just going to have to, I think, go back and forth like this. So here's the overlap between the two states. It's proportional to a whole lot of overlaps between the scattering matrix and the lower slit and the upper slit, like this. Suppose n particles scatter. This is a matrix element, right? And therefore is absolute value has less than 1. And therefore you have something less than 1 to the nth power. It goes to 0, and that's decoherence. Okay. Decoherence is not some rarefied thing like in a special, it's widespread in the universe. Consider, this is an example from Yosensei in '85. Here's a picture of a dust grain in interstellar space between 1 millimeter in size. And let's suppose it's in a superposition. I never know how to draw a superposition, but here two, which are separated by a few millimeters. So it's one dust grain in a superposition of two positions. The relative phase is between these just from the scattering of the microwave background radiation, the 10^11th microwave background photons, like in the previous example, that scatter every second, right, is, it only takes a nanosecond for the whole thing to decohere, for those two alternatives to be different. Measured alternatives decohere. In a measurement situation, a variable that's not normally decohering becomes coupled to a variant of an apparatus. So suppose here's some picture of an observer trying to measure whether particle went through the upper slit or the lower slit. There are detectors here. Make the measurement. The measurement is in interaction with this, and the measured variable decoheres and can be assigned probabilities. We ourselves have to decohere, right? Suppose we're living in a superposition. An important thing to mention here is that observers are part of the system, not outside looking at it. So if you want to discuss experimental physics, you have to discuss it from the inside of the universe as a correlation between two systems, the apparatus and the system being measured. And it can be described that way. So we ourselves have to participate in this decoherence. Well, we haven't exactly done experiments like that, but there have been experiments on very large macromolecules. For example, here's one by Lisa Hackelmüller et al. It's essentially a two-slit experiment. Of course, the apparatus is much more. And this has a fairly high atomic weight, right? And here's the interference fringes. that follow from that experiment as characteristic of quantum mechanics. We haven't yet sent a cat or ourselves through a two-slit experiment, but it's not impossible. So in principle, we could build a very large two-slit experiment and send ourselves through it. That's not that's not impossible. We haven't done it, right? But it shows you quantum mechanics. So that's as much as I want to say about quantum mechanics. It has these problems and ambiguities which people are working seem much less serious when it's viewed as an approximation of decoherent histories. And we'll go with that. I now want to talk about classical behavior in quantum mechanics. In quantum mechanics, the classical behavior isn't given. Right? There are many, after all, a quantum system behaves classically when it's stated Hamiltonian, predict high probabilities for histories with correlations in time that are governed by deterministic laws. That's as true for the flight of a tennis ball as for the Earth around the sun, or for a cosmological space-time geometry. It's an obvious fact of the laws of classical physics hold on a very wide cosmological scale. Shortly, for example, in a theory of quantum gravity, we have classical space-time, that is obeying the Einstein equations, very shortly after the Big Bang, 10 to minus 43 seconds or so. So that's the basis for the so-called quasi-classical realm, the empirical fact that there's a wide range of time, place, and scale on which the laws of classical physics apply. In quantum cosmology, we have to explain that as our feature of our specific universe from its particular initial conditions and dynamics, from the dynamics inside. I'm not going to, I'll just run through what the argument is in the hopes that it's without much detail. So the state of the universe in quantum gravity imply classical space-time in some domain, let's suppose. Then local Lorentz symmetries imply conservation laws, conservation of energy, momentum, number. Sets of histories defined by averages of densities of conserved quantities over small volumes decohere. You can calculate that. Approximate conservation implies quasi-classical variables are predictable despite the noise from decoherence, classically predictable. And local equilibrium implies closed sets of equations of motion governing classical correlations in time. I want to say a word about multiverses, since that's a simple, manageable, discoverable quantum state of the universe will not predict one unique classical history with all of its complexity. If it did that, the initial quantum state would have to contain somehow within it all the complexity about the universe we see today. Rather, it will predict ensembles of possible classical histories with probabilities. The ensemble is a multiverse, right? In the sense that it's something that's predicted by quantum mechanics, probabilities for a large number of things, only one of which is observed. That's what we mean by our quantum multiverse. And if the constants of effective theories vary from history to history, quantum mechanics predicts the probabilities for the constants of nature measured in that quantum state. Anthropic reasoning, as it's called, is therefore automatic in quantum cosmology. Suppose we have some data D that describes our observational situation, right? Like who we are, right? Human beings, what kind of apparatus they built, what kind of telescopes they looked at the microwave background radiation, and so forth. We're interested in a probability from that data in predicting observations. But if, but by Bayes' rule, that's going to be proportional to the probability of the data given the observations. So if we can't exist, this probability is 0, and so is this one. So if we vary constants, right, we will find that only some constants are consistent with the theory H and so on. So anthropic reasoning follows from treating observers as physical systems in the universe. It doesn't require a principle. It's not an option. It's not a subjective course. Well, I've talked a lot about the wave function of the universe without exhibiting one. And I'm going to exhibit my favorite one, which is the no boundary wave function of the universe that we have from work with Stephen Hawking. There's not enough time left to describe to you exactly how that works, but I can give you a scorecard for how successful it is. Does it predict classical Lorentzian spacetime? Classical spacetime, which we see in cosmology? Yes, it does. Does it predict that spacetime is homogeneous and isotropic, features of our universe, and inflating? Yes, it does. Does it predict that fluctuations start out in the ground state, giving rise eventually to large-scale structure in the galaxy distribution in CMB? Yes, it does. Does it predict errors of time? Yes, predicts the entropy is low, it starts to grow, CMB large-scale structure, isolated systems. Then that's what it does predict, and we hope that it predicts, for example, the number of large and small dimension, given a theory that allows that, like string theory, complexity from. Okay.
Professor, try the full screen.
Full screen? This is full screen?
Yeah, the next time you go there, just choose the option below, but that's okay. Sorry.
Where would I find the option? Yes, I understand what you mean now. I did that. Okay, let's see. All right, this looks better. It didn't get that nasty thing at the bottom. Thank you.
Great.
Okay. Ordinary quantum mechanics is what is called for an emergent feature in cosmology. The usual quantum mechanics of Hilbert space of states evolving unitarily through space-like surfaces on which the states live requires, first of all, a classical spacetime to define those surfaces and the evolution between them. But classical spacetime is not available all over the universe, not near the Big Bang, for example, cosmology again, and maybe not in evaporating black holes. Rather, classical spacetime and usual quantum mechanics emerge together from something deeper, and the obvious question is, what is that? What is that question? Well, the answer to that question is the decoherent histories, which I've just been describing to you. But one, let's see. Having described decoherent histories to you, I'd now like to describe getting beyond decoherent histories. Why should we worry about that? We have a theory, it seems to work, right? Why do we have to get beyond decoherent histories? One experiment which we could never do is to superpose the state of the universe with some other state. It's experimentally impossible. So that is a feature of decoherent histories, quantum mechanics, and Copenhagen quantum mechanics, and so forth. But if there's only one state, why do we need the linear principle of superposition which underlies all these thinkings of quantum mechanics. Behind that, I should also mention that in the history of physics, there are a lot of our most famous people have thought that Copenhagen quantum mechanics and our successor decoherent histories has to be modified. Certainly Schrödinger thought that, Einstein, Roger Penrose, Anthony Leggett, Hooft, and Steven Weinberg. So the question is there something deeper than quantum mechanics for the universe as a whole? One direction to move is in the direction of quantum gravity, which I haven't discussed so far. Familiar classical quantum theory assumes a fixed classical space-time, but in quantum gravity, space-time is not fixed. We need, for Copenhagen quantum mechanics, a fixed classical space-time just to define the key that occurs in the Schrödinger equation. But in quantum gravity, there's not one fixed space-time. You might have one space-time where 2 points are separated by time-like separation, and another where they're separated by a spatial separation. And in the very early universe, space-time geometry is fluctuating without definite geometry. So something beyond decoherent histories is needed for quantum gravity. Histories don't have to describe, the key to this is histories don't have to describe evolution in space-time, but can describe evolution of space-time, change the variables. Quantum mechanics is not operating in an arena of classical space-time. Classical space-time is part of quantum mechanics. So I won't have time to describe this, but you can derive a four-dimensional generalized quantum mechanics of space-time geometry, where the fine-grained histories or four-dimensional histories of space-time geometry and matter fields, where the coarse grainings are partitions of the fine-grained histories into four-dimensional diffeomorphism and variant classes, where the measure of interference is defined by a decoherence functional of four-dimensional histories. The only trouble with that, it doesn't have any 3 plus, not a trouble, but it doesn't have any 3+1 formulation in terms of a space-like surface, except in its classical limit. Okay, so this just repeats this. Classical spacetime is not available all over the universe, but near the Big Bang, and maybe not evaporating. What is it? Something different? Well, we are working on that. There's still open questions that I would like to ask you about. We don't yet have, in a theory of space-time geometry, right, a really diffeomorphism invariant of coarse graining. We would like to know, right, what the distance between different geometries are. Quantum mechanics supplies probabilities to individual members of decoherent sets. And some information has to be lost to have any information at all. So here are two geometries, the famous apple and the oranges. How far, what if we wanted to coarse grain, right, sets of histories of geometry? We would need to know to bundle them up, right, we would have to have a measure of how far one is from the other. What's the distance between these two geometries? Well, I have some ideas, but it's an unsolved problem. What is the mechanism for decoherence of a set of alternative histories of geometry? Well, I don't know what that is either, right? Like the interaction with an environment that we discussed earlier. At any rate, I hope you could solve those problems for me, but here's my conclusion. The modern formulation of quantum mechanics helps us to understand the Copenhagen quantum mechanics of measurement situations in an approximation yet more general, in a yet more general quantum theory of the universe. So we can derive Copenhagen quantum mechanics from a more general quantum mechanics that's decoherent histories. Our quantum universe both now and at the beginning, when there were no observers. The quantum mechanics that I've just so briefly discussed doesn't rely on observers. It helps us to understand the nature of final theories as not just being a theory of dynamics, right, regularities in time, but of regularities in space, that is requiring both something like a Hamiltonian and something like a state. And it describes our place in the universe as observers in the approximation of Copenhagen quantum mechanics. And it gives us a quantum mechanics for quantum gravity. There's still much to do to work out the consequences of cosmology for quantum mechanics. Here's a paper with many references and to these extremely interesting problems. Thank you very much.
So thank you, Professor Hartle. I ask you to all turn on your microphones for us to thank Professor Hartle by clapping our hands for him to see that that's 100. Turn off the microphones now, please, because the sound is very, very intense. Yes, thank you.
Thank you for that.
So we will start with the questions. So people have two options. One is to write down their questions, especially if you saw that your microphone is not working well. I ask you to please write down your question, and I can read it for you, okay? For those who the microphone is working okay, and they want to make the questions themselves, just write down. Oh, this microphone is very high. Let's turn it off. Jadir? Yeah. Parto, I think your microphone is very high. So I ask you to please write down your question. So before it was a participant. So before I start with the questions, giving time for people to write it down. So let me just tell you that we had, as I said, over 160 people around watching you. And from more than half of the Brazilian federal units that compose from all, we have 5 regions from north to south, west to east. So all of them represented here. The biggest Brazilian universities, I think, have their representatives listening to you, obviously mostly people that work in the area. And not only Brazilians, we had people from England, India, Portugal, Spain, Sweden, and US.
It's amazing.
It's
how did it work?
Yeah, it works. It really works. We're very happy with that. So let me start then with the first question written down in the chat by Giorgio Torrieri from University of Campinas. An idea related to consistent histories is relationalism. The fact that quantum mechanics describes not the system X, but the system X with respect to the observable Y. In this respect, cosmology includes causality disconnected regions where X and Y are always independent. So can such horizons be considered as source of decoherence?
I don't think so, right? That is, you're talking about depends on what level you're talking about. If you're talking about quantum gravity, where the space-time is fluctuating, right, quantum mechanically, then I don't think we have a fixed notion of horizon. There are horizons in different spacetimes which have quantum amplitudes, and in quantum gravity, they would have different probabilities. Right? So we don't have a universal mechanism of decoherence. On the other hand, we need decoherence, right, in order to have that situation where there are many classical spacetimes, right, not interfering with each other. So I don't think there isn't any one notion in quantum mechanics of a history. So we need a mechanism, right? And well, we can think of various mechanisms, and of course I'm working on that, but at the moment there are no, it's something that's an open problem.
So, okay, thank you, Professor Hartle. Thank you, Torieri, for the question. Now we have a question from Adriano Braga Barreto. How relevant can the scale invariance be in the search for a quantum description of the universe?
In the scale invariance of the Hamiltonian? Which scale invariance?
Adriano, do you want to complement yourself? He says his connection is very bad. Go ahead.
Yeah,
it's not so bad.
Yeah, I mean a theory that theory of the dynamics of the universe that are invariance, that have invariance with how can I say, with respect to the Lagrangian. For example, another theory, another theory with scale invariance, neither GR.
Let me try this, right? In this lecture, right, I tried to stick, as far as gravity goes, classical or quantum, to Einstein's theory, which is not scale invariant, right? So, because there's the Planck constant basically in it. So, other theories, of course, would make interesting cosmologies. I had enough trouble working on this one, right? But perhaps there are other ones that are scale invariant.
Okay. Thank you, Professor Hartle. Thank you, Adriano. So we have a question by Satish Kumar, DH. How does the initial singularity affect the Hamiltonian and or the wave function of the universe?
Okay. In the no bound, if we start with the no boundary wave function, right, which is a quantum mechanical wave function that predicts classical histories, then in the famous picture, which I guess I can I get back to that?
Yes.
Let's see.
Present now. No, you're still presenting. You're still presenting. So you just have to click over your PDF. Yes.
Now let's see here.
The view and full screen.
Yeah, that's right.
The last option. Yes. No.
Here. This right here is the classic semi-classical approximation to the no boundary wave function of the universe. I didn't describe at all, of course, how we construct the no boundary wave function, but it's a certain Euclidean path integral. The steepest descent approximation to that is in a geometry which is Euclidean down here and has no singularity in it, and then involves Lorentzian like this. It would take a lot more work to show you exactly how that's true, but we don't want or necessarily need to have singularities where things diverge. The important point is there's evidence for singularities in the universe in the classical theory. Einstein's equations extrapolated back give you a singularity. But the region around the singularity is exactly where the classical equation of Einstein break down and have to be replaced by something. And that something is quantum mechanics, and it doesn't have a singularity, at least in the no boundary wave function like here.
Okay. Okay, thank you, Professor Hartle. Thank you, VH. Now we have a question from Nivaldo Lemos. In quantum gravity, time is most likely an emergent concept. That is, time is not defined in the Planck regime. Doesn't this mean that asking whether the universe is eternal or had a beginning meaningless?
Okay, if we had more time, I could explain to you that we have the wave function in the universe, what I'm talking about, calculated semi-classically, predicts histories of the universe, right, which don't typically go all the way back in time because the semi-classical approximation breaks down. So they predict histories that expand, and contract, and so forth, and are consistent. The main point is with our observations, because we're not back near the singularity. But your question was about time, right? So there's classical time only when you're away from the singularity. So time comes into, let's state it in a more dramatic way. Time comes in, what we mean by time comes into existence only with classical space-time, which is away from the singularity. Did that answer the question?
Okay. Yeah, I mean, he can put down in the chat, or he can speak by himself.
Yeah, well, it's emergent, like you said.
Yes, what I mean is in the quantum regime, in quantum gravity, time has no meaning.
Yeah, I agree.
Does it have a meaning? If it doesn't, what does it mean to ask whether the universe is eternal in time, in classical time, or whether it had a beginning in classical time?
Okay. Do you mean backward in time or forward in time?
Backward in time.
There's no clear meaning to that because the classical prescription breaks down in this formulation. Some different approach to the quantum mechanics of the universe than the no boundary proposal might give you something where it is eternal. But I think not in the no boundary wave function. This down here is all Euclidean. So there's no time there.
Okay.
I wouldn't.
Okay, thank you.
It's not past eternal, in other words.
Okay, thank you, Professor Hartle. Thank you, Nivaldo. Let's move to the next question by Samarpan Das. Can the beginning of the universe be understood by quantum mechanics equations?
Can the universe be understood by quantum mechanical equation?
The beginning of the universe. That's the question. If he wants to comment on that.
I didn't devote my talk to that, but here it is once again. So quantum mechanical equation. The question is, there is no beginning, right? Because beginning is a classical concept. The universe emerges after a while, this Lorentzian emergent, but you have to be careful not to mix up assuming that something you're used to, like a classical space-time with a singularity in it, is the output of a quantum mechanical theory, because it may not be, right? And it isn't in the no boundary proposal.
Okay. Thank you, Professor Hartle. Thank you.
Unfortunately, we can't go backward in time to see this. Check on it.
Okay. Now, a question from Parto Majumdar. What exactly is the relation of these decoherence histories approach with the idea of entanglement?
Okay. So decoherence occurs when it assumes entanglement, if you like, of, say, an environment, which is, remember, let's see, this, let me get out of here. Okay, here we have a little model, a toy model of decoherence, not very realistic, but it does involve entanglement between these particles, which are usually called an environment, and the system we're talking about, which is the electron going from one part to the other in the slit. So entanglement is often or generally involved with models of decoherence.
Okay, thank you, Professor Hartle. Let's then move to the next question by Achilles Lima. Does fractional spacetime or fractional statistics play an important role in understanding the universe, the early universe?
I'm embarrassed to say I don't exactly know what fractional statistics are. Therefore, I have to say to this question, I don't know the answer.
Okay, either Achilles Lima writes again or speaks by himself to clarify the question. Either we jump to the next question by Antônio Duarte Pereira Jr. Can you comment on the recent works by Neil Turok et al. Regarding the no-boundary proposal?
Yes, I can. Right. So I think Neil and I have straightened this out. That is, we've shown, right, and Neil is in agreement with this, all the calculations that are done in the no-boundary proposal are done in the semi-classical approximation. In the semi-classical approximation, there is no, to quantum gravity, which is a difficult subject, and so I always confine myself to this limit. There's no problem with defining the no-boundary wave function because it doesn't have to be defined in terms of the Euclidean path integral, which is what Neil was complaining about. It can be defined directly in terms of saddle points, right, of the Euclidean action. So there's a paper on the web with me, Thomas Hertog, and Jonathan Hallowell, right, called What is the No-Boundary Proposal? I don't have the archive reference, but if you look in there, you will see that it's just defined directly in terms of the saddle points rather than some integral which Neil was adjusting. So I think Neil is on board with this. Right.
Okay. Okay, thank you very much, Professor Hartle. Thank you, Antonio, for the question. Next question is from Professor Nelson Pinto Neto of the CBPF in Rio de Janeiro. How can the no-boundary wave function predict the homogeneity of the primordial universe among the uncountable?
Sorry, what was it?
I'll repeat again. Yeah. I'll repeat it again. How can the no-boundary wave function predict the homogeneity of the primordial universe among the uncountable possibilities of inhomogeneous geometries?
Okay, that is a good question, and easily answered, right? Roughly speaking, the no-boundary proposal semi-classically says that the wave function is given by basically a WKB approximation, e to the minus the action of the no-boundary saddle point. Right? In that particular, the thing with the saddle point with the lowest action would dominate. Fluctuations cost action and therefore have lower probabilities. That's been worked out in a lot of models. So it does predict homogeneity and isotropy.
Okay, thank you, Professor Hartle. Thank you, Nelson, for question. Achilles Lima complemented his question, explaining that he meant fractional, by fractional statistic, the statistics related to any or many body systems. And,
I don't know how that.
So, okay.
Yeah, I think I can just. I just don't know. Quantum cosmology is sufficiently difficult that we've always taken the simplest possible description of the matter. Typically, reducing it to one scalar field. So anyons and so forth, and presumably they're included in the no boundary wave function, but I don't know how. There are a lot of questions like this, right? My teacher, Gelman, used to ask me, if you know the wave function of the universe, why aren't you rich? And the answer is, it probably does predict the fluctuations in the New York Stock Exchange, but I think the probabilities for it to go up or down are like 50-50. So it might predict something about anyons and so forth, but I don't know what they are, and I imagine that they're not that important in cosmology. Well, you need to do a calculation for that. Why don't you do one?
Okay, thank you. Let's then move to the next question by Wellington Ribeiro. He first thanks you, Professor Hartle, very much for the webinar. It has been awesome, he says. He has written. I understand that as soon as systems become more complex, decoherence becomes oppressive. How can we use decoherence to study or... I'll repeat again, right? I understand that as soon as systems become more complex, decoherence becomes oppressive. How can we use decoherence to... Yeah, that's what he wrote. Maybe he can, if you, Wellington, if you want to turn on your microphone and speak, go ahead. How can we use decoherence...
Does he mean more difficult or something?
To study or predict? Yeah. So how can we use decoherence to study or predict properties or events in macroscopic systems, something like stars, galaxies, and so on?
The interactions you could, in principle, calculate, and ordinary decoherence in laboratory situations certainly has been exhibited, but not certainly on cosmological scales. So, for example, the thing that's up there now, this is a little, model of decoherence. You can certainly calculate and have two systems, an environment, and you can presumably do experiments, right, which bear on that, but it's not on the scale of cosmologies. That's an assumption.
Okay, so let's move to the next question, again by Parto Majumdar. So the no boundary proposal has been claimed recently to have quantum fluctuations within a Lorentzian path integral approach. So I'll repeat. The no boundary proposal has been claimed recently to have quantum fluctuations within a Lorentzian path integral approach and is unstable. Can you respond to that? Can you comment on it?
Yeah, I don't think it's unstable. What does he mean by unstable? Right? That is. I think I have to punt on this one. I don't really understand the question. I'm aware of the work, of course, where there's a Lorentzian integral, but I'm not aware that it could. First of all, I don't know what he means by a wave function being unstable. Predict classical instabilities, does he mean?
Yeah, maybe he can complement. The problem is that his microphone is with problems, so whenever he turns it on, it's very loud. So I prefer that if possible, he could write it down, the complement of his question. I will be grateful for that. So let's move to the next question then, by Srijit Bhattacharjee. I'm sorry if I misspelled. For a consistent formulation of quantum history of our universe, should we formulate a theoretical setup where space-time is emergent, and then only we should be able to talk satisfactorily about quantum evolutions of it? What's your opinion on that? Could you please give your opinion on that?
Quantum evolution of the wave function of the universe? Is that what he's asking?
Yeah, I can repeat the question. If he wants to turn on his microphone and speak by himself. Otherwise, I can repeat the question. For a consistent formulation of quantum history of our universe, should we formulate a theoretical setup where space-time is emergent, and then only we should be able to talk satisfactorily about... Go ahead. Well,
sorry, that was my fault. My phone started ringing.
Okay.
Okay, again, please.
Okay. Srijit, do you want to make the question yourself? Bhattacharjee. Well, I will repeat it, right?
Yeah.
For a consistent formulation of quantum history of our universe, should we formulate a theoretical setup where the space-time is emergent, and only then we should be able to talk satisfactorily about quantum evolutions of it? He wants to know your opinion on it, if you want.
Well, I can only say what's been done, right, in which the classical space-time is emergent from the saddle points, Euclidean saddle points, of the no-boundary wave function. That was this picture back here, right, of the, I should have made.
Just complementing, he wrote that he's meaning any formulation of quantum cosmology.
Any?
Yeah, that's right.
Here, it's this, right? So here's Euclidean spacetime, and here's Lorentzian spacetime that could be said to be emergent from it. But the question was, will this always be true? I don't think so. The no-boundary wave function is not the only wave function that's been proposed. For example, Alex Bienkin, right, has his own tunneling wave function, and I don't think that has this same character. So I think the answer is no if you look over the series of things that have been proposed. All solutions to the Wheeler-DeWitt equation, right? But different solutions constructed in different ways. In Alex's case, with outgoing boundary conditions. In our case, it's by the steepest sense approximation, the saddle points of the no boundary character, which have the no boundary character, as here. Different ideas, same wave function. I wouldn't sort of make any statement that it has to be one thing or the other until we see it and compare it with observations.
Okay, so thank you. We have another question by Vitor Afonso from University of Campina Grande in Paraíba. Are you aware of the crystallizing block universe? Ideas of George Ellis, where the... Okay.
Unfortunately, I'm not.
Okay. We have a couple of questions more. Jorge Castineiras from my university, Federal University of Pará in Amazonia. Thank you for the wonderful seminar. Do you know the degrees of success in trying to describe the collapse of the wave function during measurement by time evolution, described by the Schrödinger equation of a system composed by the quantum system, the measurement apparatus, and the environment? Wouldn't it be relevant for the application of quantum mechanics to the whole universe without the need to consider an external system?
The collapse of the wave function is, in ordinary quantum mechanics, is usually said to occur when the system is measured. But there's nothing outside our universe that's measuring it. So I don't think it's relevant. Rather, what we describe is inside the universe, the correlation between two systems, apparatus and a system being measured. So measurement can be described And then perhaps the individual wave function of the system being measured might collapse. But the second law of evolution, the collapse of the wave function, is very difficult to find experimental situations for. For example, it says that if you measured some property of an electron, after the measurement was finished, right, then it would be in a state that is the projection of the measurement outcome back on the electron state. But that's just false, right? Realistic measurements don't leave the system in a projected state. They typically leave, for example, the electron I just discussed, and sort of entangled with a whole bunch of other things in the apparatus. As, for example, if you took my two-slit experiment, right, and looked at that electron as it went through, and then it hit a screen, and we determined where it wound up on the screen, the electron is suddenly not localized there. It's entangled with all the rest of the stuff in the photographic plate. So even in ordinary quantum mechanics, I don't think it's a very universal fact.
Okay, thank you, Professor Hartle. Thank you, Casillas, for the question. So we have one last question. Before I do it, I'll ask for those, so we are close to the end, I'll ask for those that did not write, have not written yet their names and the places they are watching the seminar. I ask them to please do it for us to have a registration of that. And now, Professor Hartle, we have last question, as I mentioned to you a couple of days before. So we have a young boy from Portugal that follows us, follows our webinars, and he likes to pose some questions. And consider that this question is posed from a boy, a 12-year-old boy. Mm-hmm. And he's asking, how can such a big mass as the universe be hidden inside or be contained inside a volumeless site? He's asking for you to give him some inputs about singularity.
Is he asking, do you think, how this point down here came? So the universe, by definition, is, let me try this. The universe, by definition, is everything. Right? So it's not inside something. But that doesn't mean it doesn't have a size. Right? So there's a size of the universe, right? Because like here, if the universe is closed, there's a kind of volume, and it can expand and contract. So you could say that it was in some voluminous thing if it contracted to zero volume, I guess. But I don't think it's a very useful idea.
Okay, so thank you very much, Professor Hartle. And I'd like, we have, for you to have an idea, we have still around 100 people listening to you. And I'll ask them, before we end this excellent webinar, I'll ask them all to turn on their microphones and thank you by clapping their hands. And after that, we end the session. Thank you very much again, Professor Hartle. Thank you very much.